Valence shell electron pair repulsion theory is basically just negative areas repel each other. So if you can see here, you can get some balloons, and if you just put the balloons there and throw them around, they'll end up being in this pattern here, which is 180 degrees. If you get three together, they'll form this plane. They're trying to be as far away from each other as possible, so that's 120. And then they'll form this tetrahedral where these angles here are all 109, uh, and so 109.5. And so you don't need to learn these things. Like it's important to appreciate it. So anything in the period three or lower can break the octet rule. So we can have five and six structures here. That's on your syllabus. Um, and beryllium and boron, they're too small, so they can't actually fit the octet and can't actually fit four domains in them. All right, so just be aware of that. So you've just got to use the proper terminology. It's basically just electrons are trying to get away from each other. Okay, and so that's the valence shell electron pair repulsion theory. So we call them domains. It doesn't matter if they're bonded or non-bonded pairs. So there's two electrons here, but they're in bonded pairs, and these ones are non-bonded. Okay, so um, I think it's in the next slide here. We talk about the effect of non-bonding pairs. So I'll wait till then. So the electron domain is just an area of electronegativity. So it doesn't matter if there's like two or three bonds, that's still counted as one domain. And so there's three domains here. And there's actually three domains here as well. The nitrogen central bonded has four domains on there. And so the crux of this whole and this one here, we've talked about formal charge. So you're basically, this one, you shouldn't be aware of this yet because that's breaking the octet rule. And to determine that's better, we did formal charge, which is in the video. It's good to appreciate, shouldn't be needed to be used. And so these are the shapes. You notice that this actually looks like a trigonal planar, so does this one. But if there's a central atom with four coming off, that is called a tetrahedron. Whereas if this is a non-bonding pair, so technically there's only one, two, three, four things forming a shape there. And so there are the shapes you need to memorize. Bent can be angular or V-shaped is common words for that as well. But what you basically need to know is this table here in the red letters. Okay, so just before we get to there, if the electron pairs, so let's just say this is don't know what I call this one now. Maybe this one's hydrogens. There are protons here, and so the protons are pulling this electron pair. It's in a tug of war. Whereas when they're non-bonded, there's no positivity over here pulling it away, so it's much closer to the nucleus of the central atom. And because of that, its effect to push these bonds away increases. So the bonding angle is only to do with the bonding pairs. And so the non-bonding pairs, the effect is they make the bond angle decrease, on average about 2 to 3 degrees, but it all depends on which element it is, the degrees of pos and neg involved in that. So take every question at face value, but you will have to memorize those numbers there. So basically, number one, you have to be able to draw the electron dot structure, so you know how many non-bonding bonding pairs there are and where they are. Put that on this. So identify the central atom, count the number of electron pairs, non-bonding pairs, and then the shape. Um, the shape and the angles are based on memorizing this here. Now I have added. Where's my pen? I have added this thing here, which is all linear. Um, so if you draw the molecule out, you can see that there is. Hopefully, you can see the picture of it that it could only possibly be linear. These angles may not be intuitive though, especially things like these ones. So sorry, that's IB 109.5. So 109 will do. So memorize these shapes and angles, and don't think you can get away from that. You've watched this video now. Stop for 10 minutes and make sure you've memorized. Two electron domains, linear 180, trigonal planar, bent is less because of that electron bond electron pair pushing it down a little bit. Um, and this one, importantly, is water. So all the red ones have them memorized, and then we can move on. And so I've just got some examples. This is what the Molly mods look like. And the Molly mods you'll probably find, no doubt, put in the comments, are pretty much impossible to do because you've got to have you've got to have the right number of spaces in them. So hydrogen fluoride's linear, and that one's easy as well. But the carbons need to have four. All right, so you can do the proper tetrahedral shape. Notice this one here, it's a single bond that can spin and turn around. I've placed it in the place at 90 degrees to each other so that they're as far away as possible. So that would be their preferred shape, but they can turn. Whereas ethene, double bonds and triple bonds, you can't spin them around their axis. So that's important later for organic chemistry. The carbonate ion here. So this is what I'm talking about. It's hard to get one, two, three, four reds. I think we have like 20, 30 sets, and I've only managed to get a couple of these. So this is why I've done these pictures and videos because I think it's almost impossible to get the proper structures out. Um, this double bond could be written here, double bond could be written here. That's a sign as resonance. So the actual true bond length here is one and a third, one and a third. But you don't need to know that for your syllabus. But I think you should appreciate it that we're giving you just very simplistic answers and very just correct overviews. It's still going to be trigonoplanar. In reality, if it really was this angle would be less, and this would be greater. Um, but that's not the case, which is the scientific evidence for the fact that there is resonance going on here, and the actual shapes, SPDFs, are actually merging, and the waves are overlapping and interacting with each other, just like waves do. So moving on, carbon dioxide, that one's a cool one. They're at 90 degrees to be as far away from each other, and they're locked in place. Um, so water here is bent. So we should be able to give you a shape. You should be able to count one, two, three, four with two bonding pairs, and then cut the table to find the correct shape and angle. Hydronium ion, same thing as hydrogen plus, but it often just combines itself with water with the lone pair there. So that's actually a dative bond um, that goes like the electrons go over here. So that's a dative bond. So delta pos and delta neg. Learn about those soon with polar bonds, next video. Once again, this is breaking the octet rule, and formal charge will prove this one's the correct shape, but they're both bent anyway. So going by ATAR rules, that's the incorrect one's actually the one we're looking for. And ammonia and ammonium. Again, there's a dative bond there. So you really technically should put the arrow in there for that. Dative coordinate covalent bond.